Hello, so this is some brief notes on C2 Chapter 2 separation techniques, which will be coming up in your June exams for Year 8. So just a reminder of all the different places you can get information from. Obviously you can log into Caboodle and have a go at the quizzes and the tests on there. You've got your SAM Learning login, so they've got plenty of quizzes and tests and information on there. BBC Bite Size has some really great pages on there, and those of you that bought the revision guides, you've got that, and obviously your notes from lessons. The BBC Bite Size is particularly good, so if you just Google BBC Bite Size KS3 Science and click through on that, and then it's in the chemistry section. Solids, liquids, gases, that'll be a good revision for this, but we're looking at the pure and impure chemical samples particularly, so plenty on there, and then the separating mixtures, so plenty on there to work through as activities, as tests. Okay, so there's plenty for you to access. So this is just a brief run through of some of the ideas that you need to know about. So describe how particles are arranged in mixtures. So you'll remember your particle diagrams from Year 7 chemistry. Our solids, all the particles are arranged neatly in crystalline formation, so all lined up, very few gaps between them, and all the particles button up against each other, so no movement by those particles. In the liquid, this is not a great image because it shows gaps between all the particles. So in the liquid, they're still touching, but they're more randomly arranged and they're continually moving around. And then the gas, the particle diagrams show very large gaps between the particles, and then they're moving much faster. Notice that the particles themselves don't change size, so they remain the same size when you go from a solid liquids to the gas, and the reason gases are much larger are because you've got these large spaces between the particles. When we come to mixtures, mixtures are simply substances where you've got two or more compounds or substances mixed together but not necessarily bonded. So B would be an example of a pure substance, whereas A would be a good example of a mixture. You've got these what look like water molecules here, and then you've got other things, maybe oxygen molecules spread throughout the mixture. So D would be a pure substance, only one type of substance. E would be a mixture, two different types of substances, and C would also be a mixture, lots of different substances, two different substances mixed together. So you also need to explain how pure substances can be identified using melting points. So if we take a substance and we heat it up continually over time and measure the temperature of that substance, we will see the temperature rise until it reaches a certain point, and then even though we are continuing to heat it, the temperature of that substance doesn't change. This is the time when the substance is actually melting, so turning from a liquid into a solid into a liquid. So here we've got solid, and up here we've got it as a liquid. So during this time here, then the substance is melting, turning from solid to liquid, so all the energy that we're still putting into it is breaking those bonds that hold the substances together in the solid, and it's ending up in the liquid form. A pure substance will show a nice sharp melting point, so it will melt at one particular temperature. That temperature will remain the same over time, and then it'll start increasing again once it's completely melted. For impure substances, if we do the same thing, we will see the increase in temperature, and then we'll see a rather messy increase. So you'll have the solid there, you've got your liquid there, and then the melting is occurring between the same points. So we've got melting occurring between here and here, but we've got multiple substances in there, so they're all melting at slightly different temperatures. So that one would be an impure substance, and that one would be pure. Explain how solutions are made from solutes dissolving in solvents. So this is some keyword definitions you need to be happy with. So a solvent is simply a substance in which solutes dissolve. E.g. water, and then a solute is what dissolves, e.g. salt, and then a solution is when you have a solute dissolved in the solvent. Okay, so these are keyword definitions you should be able to talk about, and it's easiest to think about them in terms of examples. So sugar dissolving in water would be a good water-based solution, salt dissolving in water. Here we've got some copper sulfate, which is a nice blue crystalline solid, and it's readily soluble in water. So you can see the water here is clear and colourless. You can see the blue crystals here, and then when you put it in the water and give it a stir, the solution turns blue, and you can't see the solid anymore. So that's one of the definitions of dissolving, when the solid appears to disappear, but it's all the different particles have gone into the water and are now dissolved. You can have other types of solutions, so gases can dissolve in solvents, and a good example of that is fizzy drinks. You open your can of Coke, and it's when you look through the bottle, it looks as though there's no bubbles in there, but as soon as you open it, all the bubbles come out. So that's all the carbon dioxide which has been forced into solution under high pressure, and when you open the cap, the pressure is reduced, or the pressure drops inside the bottle, and so all the carbon dioxide comes out of solution. Another example of this is oxygen dissolving in water, which allows aquatic organisms to respire, because they can absorb the oxygen from the water. One you might have done in lesson as well, not all solvents are water-based, some are non-water-based, so acetone or nail varnish remover is a good solvent for oily substances like nail varnish remover, So the nail varnish won't dissolve in water, but it will dissolve in acetone, which is a different kind of solvent. Describe how saturated solutions are formed and explain how solubility is measured. So if we look at this picture here, we've got a solution which has been made from salt and water, and then if we keep on adding the salt, the solute at this stage, at some point the solution will become saturated. It won't be able to absorb any more of the solute. So a saturated solution is when the maximum solute has dissolved. Okay, and how solubility can be measured. So it's this unit here on this table, so grams of solute per 100 grams of water, or whatever the solvent happens to be. So the reason that we use a mass of water is that all solvents will change their volume depending on different temperatures, so we base it on a mass, and this doesn't change as temperature changes. So for an example, you could say that sugar has a solubility of, just making up a number here, 50 grams per 100 grams of water at a particular temperature. Okay, so the reason we have to state a temperature is because if you look at this diagram here, this shows the different solubilities at different temperatures. Let's pick potassium nitrate, this one here. We can see that at very low temperatures, so at 0 degrees Celsius, only 15 grams will dissolve per 100 grams of water. But if we take the temperature up to, let's say, 70, that would be here, we can see that 130 grams will dissolve per 100 grams of water. So the solubility increases very quickly with temperature, and you'll see that when you're doing the cooking. You put salt in cold pan of water, it doesn't particularly dissolve that well, but you put it in boiling water, it dissolves very quickly. So most solutes, solid solutes, will increase in their solubility as you increase the temperature. Separating the substances. filtration is one of the easiest ways. So if you've got a solid dispersed in a liquid, so sand in water for example, then the sand is insoluble, so it doesn't dissolve, and that can be easily removed from the water by passing it through a filter paper. And so you can think about this in terms of the filter paper as having little gaps within it, and then if you have very large insoluble bits of sand, and then the water particles themselves, which the salt is dissolved, the sand is dispersed in, so that's the water, then our water particles can get through the small gaps in the filter paper, so they become the filtrate. So that's the bit that the liquid that passes through. And the sand particles here, they're too large, and so they can't get through there, and so they become the residue. So that's one way of separating out mixtures. Another way of doing that is if you just have some sand in the bottom of some water. If you allow the sand to settle at the bottom, then you can just carefully pour off the water, and that's called decanting. And that's another quick way of doing it. Should you wish to get the something that might happen to be in the water, so if we had, for example, salt in there, so our water passes through the filter paper, and our salt particles, which are dissolved because they happen to be soluble, so we've got lots of salt particles passing through as well. So our salt is in our filtrate, so salt particles passing through. Then what's left over through the filtrate is salty water in here, and then we can evaporate the water. So that will be the next separation separation technique. If we've got salty water, as we can see here, then we can just remove the water by evaporation. So heating this, the water will evaporate, and our salt crystals, our salts left behind, so these are crystallizing. Okay, and this is done in hot countries. If they want to extract salt from the sea, they just have large ponds which they fill up with seawater and then block them off so no more seawater can get in, and then just leave it in the heat of the sun, and the water evaporates and the salt just crystallizes out, and then they skim it off and sell it. Should you wish to capture what's been evaporated, for example, if you're separating out inky water, for example, or if you're doing a chemistry experiment and you've produced a substance and you want to collect that substance, then you can use the process of distillation. So distillation is simply evaporation plus condensation. So evaporation first, then condensation. So here we have our mixture. So in this case we have salt water. So here the water is evaporated, and it remains evaporated until it gets into this cooling apparatus called a condenser. So cool water goes in at the bottom, cold water comes out at the top, and this is in a separate part of the condenser. So you've got a tube running down the middle, and then our particles of water, which are gas up to here, eventually they get cooled down and they turn into a liquid, so they come together as a liquid, and so you get drops of water forming, and eventually those drops of water come out into the collection flask here. Okay, so evaporation of water here, liquid turned to gas, and then the gas turning back into a liquid, and what will be left here will be salt.